Now that we've got color, we can move on to a higher level and more interesting application of abstract data types, and that's image processing. And in this immediately, you're going to be able to write programs to process things like pictures that you take with your cell phone. So we're going to work with an abstract data type that's called a picture. A picture is a two-dimensional array of pixels. Again, it's defined in terms of its set of values. The set of values is 2D arrays of pixels. And so that's what we think of a picture as being. And we're going to have an abstract data type that allows us to write programs that manipulate pictures. And so values are 2D arrays of colors. And just to get oriented, we think of this as rows and columns with 0, 0 up at the top left. And we're going to use two indices to refer to the pixel at a particular place. We have its column and we have its row. And that's how we're going to refer to individual pixels. It's got a certain width and a certain height. Just with that orientation, then we can define the operations that we're going to perform on pictures. First one is a constructor. How do we make a new picture? Well, what we're going to do is take a file name as argument, and that file name is going to be an image that comes from your camera. It could be JPEG file or other standard file format. And then once the constructor has made the image, we can think of it as a two-dimensional array of pixels. We could also create a blank one. And then we can ask for properties of the picture, like its width and its height. We can ask for the color of a particular pixel, given a column and row, as long as the column index is within the width and the row index is within the height. And we can also set the color of a pixel to be some other color. And then the other thing we can do is just display the image in a window, like standard draw. There's also a method in standard draw to display pictures, but this just displays the thing in a window. So those simple operations, again, we don't really care how the picture is represented and how the system gets these jobs done. We can work with pictures just using these very simple operations. And also we can save any picture that we've created back out to a file. So here's an example. What we're going to do is write a Java program that'll convert an image to grayscale. If we take our mandrel, and this image, by the way, is a standard image that's been used for many decades in computer graphics, so that's the one we're using. If you type Java grayscale and give that file name, then it'll give this black and white version. Interesting computation, so you can make black and white versions of photos that you take on your phone yourself if you want. So how do we do that? It's a very simple program. We get access to the Java's color module with that import, and then we just write a main that, first of all, it's going to create a new picture. And where's it going to get that picture? The first argument is going to be a file name. And so the constructor takes that file name. If it's a JPEG file, then it'll use that to create a new picture, which now we can manipulate as an array, a 2D array of colors. And then what we're going to go do is go through, and for every pixel, we're going to get its color. So we'll go for all columns and for all rows. It's a doubly indexed for loop to look at every possible pixel. We're going to, our picture is named PIC, or pic, and so that's stored in a picture object. With PIC dot get, that means take that object, and then the dot means apply the operation to that object, and the get operation gets the color at the given column and row. So that returns a color, and then that's a variable of type color with a capital C. So now we're going to compute with that, and what do we want to do with that? We want to just go to our luminance library and get the toGray method that we just did that computes the grayscale value. Put that in another color, gray, And then in our picture, we'll call the set method to change the color of that pixel at that column and row index to that gray value. And that's it. And when we're done with those for loops, just show the picture, and that's it. An extremely simple program to go ahead and compute any color image into a black and white image. Now let's look at some more examples. Just to warm up to do some more interesting computations, we'll do a little series of pop quizzes. So let's think about what's the effect of this code. This is a very easy question. For all the pixels, what we're going to do is take our picture and set the pixel at column and row to the color that you get from getting the pixel from column and row. Well, that one obviously does nothing. It just shows the picture. But that's a warm-up for let's do something, try to do something more interesting. This one's not so easy. So now what we're trying to do is set the one at column, and rather than row, we do height minus row minus 1, so the one at the top becomes the one at the bottom, and so forth. So it looks like we're trying to turn the picture upside down, but doesn't really work. It kind of takes the top half and puts it on the bottom half, but then it's already done because it's overwriting the same picture. So that's a bug that's worth thinking about. What we need to do if we want to do this upside down thing is create a totally new picture, and so that's the answer to this question. We're going to take our source picture, which is the one that we get from the file name in the command line. We're going to get the width and the height of that picture, and then we're going to create another picture, the target picture, and we'll create a blank picture of the same width and height. And then we go through for every pixel and we set the pixel in the target picture. There we can do the rows upside down to the color that we get from the source picture and then show it. So that one actually does make an upside down copy of the image. So, but lots of our pixel processing programs have this same concept of we go through for every pixel and set it to some value. Maybe it's a value that is a function of the value in some source. So this is a classic example, a scaling filter. And this one is useful in lots of contexts. So what we want to do is write a Java program that will scale an image, kind of arbitrarily and independently. So if that's my mandrel, then it's a 300 pixel by 300 pixel image. Maybe I want to make it bigger, like 500 by 500. Or maybe I want to squash it, make it 600 by 200. Or maybe I want to make a tiny one, or a long up and down one. So I want to arbitrarily scale the image, and there's lots of applications where we need to do this. Maybe to get an image to fit in a certain space, and maybe scaling it just by a little bit extra in one dimension or the other just to make it fit, and it wouldn't be noticeable. So that's anyway our computational challenge. Let's scale an image. Now, for example, let's say you had to cut it in half. So one way to do it is to just downscale by just deleting alternate rows and columns. So that example, you're going to lose some detail when the picture isn't big enough, but anyway, that's an option. Or you can upscale by doubling, so that's to make a picture twice as big, just replace each pixel with 4 copies of itself. And then if you were to do that back and forth, you don't really get quite the same image back. But that's going to be an issue when we do scaling. Fortunately, our pictures are at high enough resolution that there's maybe not, these effects are maybe less noticeable than you might think. But we want to do this in a systematic, organized way. And so here's a strategy that will get this scaling done. So if we got our source width by height and our target width by height, what we're going to do is just take the ratios of those differences to get ourselves a column and row index. But the key thing to do is to set up the computation that really what we want is we want each target pixel to have a specific value. And so we're going to do that by scaling from the source, making sure that we get a defined pixel value for every row and column in the target. And to do that, we just take whatever row index we get by scaling the target row index, and whatever column index we get by scaling that and doing the transformation. So it turns out to be a pretty simple program. We take as input in the first command argument the file name, which is the picture that we want to scale, and then we take the width and height that we want out of that picture. We create a new picture from the file, and that's our source. And we create a blank picture of size W by H, that's our target. And so now what we want to do is for every pixel in the target, we want to figure out where we're going to have to go in the source to get a pixel that's close to where it should be according to the scaling. And so that's what we'll do. We'll get some column and some row in the source. We'll get that color of that pixel and then set our target pixel to that color. That way we've got a good color for every target pixel. And then we show it, and it takes a little thought, but that's a pretty compact program to get this scaling job done. And works fine for our mandrel. This one is worth studying, but it's indicative of the ability that we have with image processing to really do quite a bit with our images. All we need to do is make sure that we set every pixel in the target to some color. And people have studied lots and lots of different transformations that we can perform on pictures, and you'll have, I think, some fun doing this with pictures that you've taken from your cell phone. So you can separate out the RGB colors. That's a thing called a swirl filter. That's a wave filter, glass filter. All these types of transformations are actually not so difficult computationally. So all kinds of effects like this, and you can see how to do them on your own pictures in the book site or in the book.